Modern engineering relies on materials that can survive the absolute limits of physics, from high-capacity batteries in our pockets to the brutal heat of exhausts and intense friction inside industrial engines. Many of these disparate technologies share a single, invisible dependency, Group 9 of the periodic table, also known as the Cobalt family. These elements share a baseline set of physical traits. They are all transition metals, noted for being exceptionally tough, solid at room temperature, and possessing a lustrous silvery white appearance. Their industrial utility is a direct result of their geography on the periodic table, specifically within the d block. Inside their outermost shells, they possess d orbital electrons. This specific arrangement allows them to facilitate chemical bonds efficiently, providing their characteristic strength and catalytic properties. By understanding this atomic layout, we can see exactly how human engineering manages energy, chemistry, and extreme physical forces. The descent begins at the top of the column with the lightest member of the family, Cobalt, atomic number 27. While famously used to create the blue glass and pigments found in historical artifacts, Cobalt's modern role is as a technical requirement for high-strength magnets and the lithium-ion batteries powering our electronics. Moving down one row brings us to Rhodium, atomic number 45. Here, both the atomic mass and the rarity of the metal increase significantly. Rhodium utilizes its d orbital electrons to serve as a vital catalyst, primarily within vehicle emission control systems. Inside a catalytic converter, Rhodium exists in a brutal environment of constant heat. Its surface provides the site where toxic exhaust molecules are forced to collide and break apart into less harmful gases. Shifting down a single row moves to focus from energy storage in batteries to an environmental shield capable of facilitating reactions in high-stress chemical environments. The third natural step in the group is Iridium, atomic number 77, which represents the extreme physical limit of the family's durability. Iridium is virtually immune to corrosion. Because of this, it is frequently used to harden other durable metals like platinum for use in specialized electrical contacts. At the very bottom of the column, the pattern of durable, useful metals breaks. This is meitnerium, atomic number 109. Meitnerium is a synthetic element. It is highly radioactive and exists only for a few milliseconds in a laboratory setting before it fades away. This creates a unique contrast. Despite having the same d orbital electron structure as cobalt and rhodium, meitnerium has no commercial or industrial uses. The descent down the column begins with a workhorse of modern energy and ends with a fleeting, artificial phantom, demonstrating the point where the family's shared atomic structure meets the physical limits of nuclear stability. When we look at cobalt, rhodium, and iridium together, they form a unified spectrum of high-performance materials. While meitnerium marks the boundary of what can be synthesized in a lab, the three natural elements above it provide the physical materials required for modern infrastructure. The vertical alignment of these elements provides a technical blueprint. If you understand the shared traits of the column, you can identify the specific industrial problems these elements are suited to solve. The shared d orbital configuration is the specific mechanism that allows us to store energy in batteries and scrub pollutants from the air. Whenever an engineering challenge requires extreme resistance to heat, corrosion, or wear, the solution is almost always found in the unique properties of the Group 9 elements.